Hello guys, I am Francis Dominic Lumangkas. I'm presented to you the surface water hydrology runoff models. But before that, we know first the objectives of this presentation. First is to know the definition of some terms. Second is to know the history of runoff prediction. Third is to know the importance of modeling runoff. Fourth is to know the basic structure for runoff model. Fifth is to know the equations of each basic structure models. Sixth is to know the different categorization of spatial structure processes. Last is to know the two ways to calibrate runoff model. So first is what is runoff? Runoff is a precipitation that does not infiltrate into the soil and runs across the land surface into surface waters such as streams, rivers, lakes, or other reservoirs. So this is the illustration of the water cycle or hydrological cycle. As you can see in the red arrow, that is the surface runoff or runoff. Surface runoff varies time and location, with about 1/3 of the precipitation that falls on the land turning into runoff, while the other 2/3 is mag-evaporate, mag-transpired, and mag-infiltrated into the soil or land. The history of runoff prediction. Early hydrologists calculated surface runoff with limited data and simple computational techniques. The first widely used runoff method was the rational method published by Thomas Mulvaney in 1851, which used rainfall intensity, drainage area, and a runoff coefficient to determine the peak discharge in a drainage basin. The coefficient determining the relationship between the amount of rainfall and runoff was studied heavily and led to a graphical technique for estimating the amount of runoff. Only see Thomas Mulvaney who published the rational method. The other one is the basic flow components of the runoff hydrograph, which is the separation of the quick response runoff and the base flow. What is runoff model? Runoff model is a mathematical model describing the rainfall runoff relations of a rainfall catchment area, drainage basin, or watershed. More precisely, it produces a surface runoff hydrograph in response to a rainfall event represented by an input as a hydrograph. So why is it important to model the runoff? Modeling runoff helps gain a better understanding of hydrologic phenomena and how changes affect the hydrological cycle. Runoff models visualize what occurs in water systems due to changes in pervious surfaces, vegetation, and meteorological events. Modeling surface runoff can be difficult, for the calculation is complex and involves many interconnected variables. There are three basic structures for runoff models. First is the empirical models, second is the conceptual models, last is the physical models. Empirical models. Empirical models, sometimes called data-driven models, use nonlinear statistical relationships between inputs and outputs. They are observation-oriented and depend heavily on input accuracy. So, ang empirical models is gamit kaayo ni siya if ang other outputs is dili kailangan. The general governing equation for empirical models is a function of inputs as shown. Q is equals to F quantity x, y, where Q is the runoff output and x, y are input datasets of rainfall and historic runoff. This illustration shows the relationship between the rainfall inputs and runoff outputs. As you can see in the small rectangle, na ay formula dira. Sorry kung dili kayo maklaro. Q is equals to P minus 0.2s squared all over P plus 0.8s, where Q is the runoff, ang P kay precipitation, then ang S is the retention parameter. Napoy IA dira, which is ang IA is the initial abstraction. So next is the conceptual models. Conceptual models interpret runoff processes by connecting simplified components in the overall hydrological process. They are based on reservoir storages and simplified equations of the physical hydrological process, which provide a conceptual idea of the behaviors in a catchment. So this is the governing equation of the conceptual models. ds over dt is equals to p minus et minus qs positive negative gw, where ds over dt is the change in reservoir storage, p is precipitation, et is the evapotranspiration, qs is surface runoff, and gw is groundwater. So ang illustration shows the PARL and D as an assembly of multiple storage processes following the water balance equation. So next model is the physical model, also called process-based or mechanistic models, are based on the understanding of the physics related to the hydrological processes. The general physics laws and principles used include water balance equations, conservation of mass and energy, momentum, and kinematics. So this is the governing equation of the physical model. dH over dt is equals to PO minus I minus EO minus QOC plus summation of QSIJ, where dH over dt is the water depth at time t, QSIJ is the surface flow from element I to J, then ang PO is the precipitation, I is the infiltration, ang EO is evaporation, and the QOC is the interaction between overland flow and channel routing. So the model of structure of the physically based Penn State Integrated Hydrologic Modeling System or PIHM. Ang kaninga illustration, it shows physical movement of water through each triangular irregular network via overland flow, evapotranspiration, infiltration, recharge, and groundwater. Next is the spatial processes. Spatial processes in runoff models provide a means of representing the catchment for modeling. They are based on input data and how runoff is generated and routed over the catchment. Variability in geology, soils, vegetation, and topography affect the relationship between rainfall and runoff within a catchment and should be considered in modeling. So naay tulo ka categorization of spatial structure processes. First is the lump models, second is the semi-distributed models, and last is the distributed models. So this is the illustration of different spatial processes. So ang kanang letter A is mo ng lump models, kanang letter B is mo ng semi-distributed models, ang kanang C mao ng distributed models. Lump models treat the catchment area as a single homogeneous unit. Spatial variability of catchment parameters is disregarded. A lump model is designed to simulate total runoff and stream flow at the outlet point, not specific flows within a catchment. So ang lump models include a lot of assumptions about the hydrological processes. Because of these assumptions, lump models have a tendency to over or underestimate runoff values. there is spatial variability in rainfall across a catchment which is not captured. So next is the semi-distributed models. Semi-distributed models are variations of LAMP models with features of distributed models. They can consist of a series of LAMP parameters applied in a quasi-spatially distributed manner. The model process divides the catchment into smaller areas with different parameters for each. Most models are semi-distributed because of data availability and range in the spectrum between LAMP and distributed models. A semi-distributed model can have data that are separated within the catchment but homogeneous within the sub-area. Next is the distributed models. Distributed models are the most complex because they account for spatial heterogeneity in inputs and parameters. Fully distributed models separate the model process by small elements or grid cells. They are also structured like a physically based model, which makes them more relatable to the actual hydrologic process. Ang problem sa distributed models are their demands for distributed data and calibrated parameters for every grid cell. If the data are not fully distributed, so ang estimation using weighted average are used to extrapolate data. Ang another weakness pa sa distributed models kay ang computational time needed to run one simulation which can vary from 1 minute to several hours. So, magdepende sa input data, sa catchment size, and computational constraints. So, ang distributed models are not widely used. Next is observed data. Observed runoff data are derived from detected stream discharge data by dividing discharge by upstream contributing catchment area. So, this is the graph of observed data. So, it shows a hydrograph observed discharge data separated into model components of base flow, through flow, and overland flow. Next is the calibration and uncertainty. For runoff models, to efficiently simulate runoff in a catchment, calibration to the specific catchment is required. Calibrated parameters are adjusted to fit observed data for better output. So there are two ways to calibrate a runoff model. First is the manual trial error method. It uses observed historical data to adjust each model parameter, and parameters are then compared visually so that to determine if another trial should be executed. Next is the automatic optimization algorithms. These are computer-based methods designed to speed up calibration time. So, with a larger number of parameters, there's a greater possibility that some parameters become too site-specific. Models with many parameters have less chance of finding the best parameter than modules with fewer parameters. So, discussion. Surface runoff, a major process in the hydrological cycle, connects precipitation to surface reservoirs. Changes in vegetation, soil moisture, meteorological components, and surface conditions alter runoff. Some models are better at considering these changes by computing runoff in a distributed spatial process. Simulations of surface runoff can help us understand how changes in the environment affect runoff and the hydrological cycle. Our classification of rainfall runoff models by model structure and spatial processes shows different types of rainfall runoff models and ways in which we distinguish models. So thank you for listening, guys. God bless.